In the last session, we are discussing about this crystalline silicon solar cell, right? And yeah, we discussed several concepts to increase its efficiency, right? And then we stopped in this. We are discussing this anti-reflection coating, what should be the thickness, and then we discussed how to reduce the recombination losses, and we discussed about this anti-reflection coating on the top, and we can use the silicon oxide layer and silicon nitride both, right? Any of them we can use for anti-reflection coating as well as surface precipitation layer, right, in the solar cell on the front surface, right? So front contacts, or sorry, front layer, until this we could optimize, right, that why we are doping N plus and the purpose of anti-reflection coatings. Now how we put the electrode, right? This thing we discussed earlier. We'll just quickly brush through once again that what should be the optimum thickness of these bus bars and the finger bars, or the fingers, right? This thin metal grids. So there are two types of metal grids, right? One is the thick bars called bus bar, which basically connects to the external circuits, and these fingers which collects the electrons from the wafer and then sends to the bus bar, right? And this configuration is used to minimize the shredding loss, right? Because light has to enter into the cell, right? From this surface, from the front surface, right? So for that purpose, yeah, we can see this diagram, right? So this front surface, so there is a trade-off between this thickness and the or thickness of this contacts, right? This metal contacts or these grids. Sometimes we call this one as this thin one. We call it as finger electrode, right? Or fingers. And these are the bus bars, right? The thick one. So this the thickness of these fingers or the bus bar and the shredding, right? If you increase too much this finger thickness, then we'll have lot of shredding loss, right? The sunlight cannot enter, right? So there is a trade-off between these two. So let's try to understand first the finger spacing. So I'll just draw the top surface of the solar cell, and I'll just draw two fingers to understand this, or a couple of, okay. Okay, so first thing is finger spacing. That is, so what I mean is these are the fingers which are essentially made with thin metal films, right? Generally they could be aluminum or silver metal films, right? So these are opaque to the sunlight, so they will shred the sunlight, right? So there will be shading, so the sunlight cannot enter into this region, so it's a loss for us, right? Those photons will lose off. Okay, so finger spacing, so this spacing D, right? So if we increase this finger spacing, then what is happening is our shading loss will decrease definitely, right? Shading loss. So in this curve we have the power loss. So shading loss is decreasing because we are increasing the D. So more sunlight can enter, right? Shading is decreasing, but the contact resistance, right? Emitter. So this top layer is our N type, right? It is also known as emitter, right? So this is our this is the N type emitter, right? So the resistance between this emitter and this metal contact, it will increase, right? Because if you increase this finger spacing, so number of fingers will be less, or the contact area between this emitter or N-type semiconductor and the metal, the contact area will reduce, right? We know the resistance R equals to rho into L by area, right? Rho into L by A. So as we increase the finger spacing, the contact area will reduce, right? So eventually our resistance will increase. And one more thing is, if you go for very thin fingers, right? If you go for very thin fingers, then also the then the next one will come. So first let's finish up this one. So if you increase the finger spacing, our contact area between this emitter and the metal, this area is reducing, right? So if you increase D, the area decreases, the contact area decreases, so the R increases, right? So we'll have a very resistive contact. So here you can see this this line. This indicates the resistive emitter, that is the emitter resistance is increasing, and because of that the overall loss is increasing, right? So this is the power loss, right? So we are losing more and more carriers, or overall the electrical power it will reduce, or efficiency wise also it will reduce. And the contact resistance also, you can see the contact resistance is increasing, this curve. If contact resistance increases, this resistance actually falls in series with the solar cell equivalent circuit, right? We have seen the equivalent circuit, right? So this contact resistance falls in series. Now when we try to operate the solar cell, there will be voltage drop, right, in the series resistance, so which essentially gives us lower VOC, lower output, right, lower efficiency. And there is a trade-off between these two, right? So one thing is shadow is decreasing, which is good, but contact resistance is increasing, right? So in that case power loss is increasing, and here it is decreasing. So if you sum these two curve, this shading loss and this emitter resistive emitter loss, then you will get this blue curve, this curve, right? This is the total one. So you can see there is a trade-off between these two, and we want minimum power loss. So here we achieved the minimum power loss, right? This somewhere here. So if you just take this one, so this is the optimum finger spacing for this particular configuration, right? So we can finalize it. And next is the finger width. So this finger width, let's say this one, let's say W, this one, right? This finger width, if we keep increasing it off, then what will happen in the area, if you expand the area will be width into the height. So height, it is in three-dimensional space. If you see, this finger has a depth also, right? Inside the metal it is buried, right? So let's say this is W, this depth is the height, H, right? So cross-sectional area is W into H, right? Now a finger width, this W, we can increase to reduce this resistance, right? So this resistance is, we are talking about this finger resistance, okay? So L also let's define. So this is the length of this finger, right? So this is the L, right? So what we can do is, we need to minimize this R, right? We can increase this W, right? We can increase the W, then we can minimize this R. So as you can see here, the red curve, right? As we increase the finger width, the resistance is decreasing, or the power loss due to this resistive emitter, it is decreasing. But as we increase this W, we are increasing more and more shading, right? More and more metal area. So less open area for sunlight to enter. So shadow will increase, right? If you increase the finger width. So one thing you can consider here, that if you want to reduce the resistance, we can increase the H, right? This height. Also we can increase to reduce this resistance R. Yeah, it's true, but there is a limit. We cannot buried or we cannot use very thick metal contact, right? Because essentially this is reducing, if you see side perspective, it's something like this, right? So this height we cannot increase too much, right? We will go near to the junction. So there is a limit in this H, but we can utilize this, uh, you know, H as much as possible. Of course, we cannot go and deeper much inside, right? We'll be touching this junction itself. And we know this top layer, the thickness is optimum is only 0.3 micrometer, right? This N layer thickness. So within that, we have to have the metal, and also there should be some space, right? So that is limited. So to reduce resistance, we can increase, play with the W, and of course we can reduce L, but again it is limited, right? If you reduce L too much, generally this fingers I didn't draw fully. It should cover the full surface, right? Because we need to collect the electrons from this N type, right? If we put half of this, then the electrons which are produced here, they have to travel, right, long distance to reach this metal. So again the resistance will increase, right? So this L is also limited. We cannot reduce too much. If you reduce, you can reduce the resistance, but the problem would be collection, right? So this L also you cannot play, and if you see this L, you can see it is spaced throughout the solar cell, right? Because we need to collect the electrons from everywhere, all the places, right? So it has to be. So L we cannot play with. Uh, so what is happening here? If you increase the finger width, of course, resistance is decreasing. So this loss is reducing, but shadow is increasing, right? So if you combine these two, there is an optimum condition here, and we can get the optimum finger width somewhere here, right? So in design perspective, these two numbers are very important, right? So later we'll see that how we draw this or how we make these contacts, right? Or uh, to, how we pattern these electrodes on the top. Usually we use screen printing technique. Okay? Screen printing technique. So we use the silver paste or aluminum paste and then do a screen printing. I'll come more details about it later on. This is much cheaper way. So we have optimized the front contact. Now what about the back contact, right? This back contact. So in the back contact, we can have similar issues like front contact we have, right? The one problem is not there. This threading and all back contact, it doesn't matter, right? We can cover the full back surface with metal, but the problem would be this, interface between the metal and the semiconductor, right? Interface between the metal and semiconductor could be full of defects, right? Because there is a sudden change in the lattice structure or in the periodicity, right? So there will be defects definitely. So to reduce that defect recombination, so if there is a interface between the let's say here, right? So this interface we can have uh, SRH recombination. Because of the defects present, we are changing the material from semiconductor to the metal, right? So there will be a lot of dangling bonds present, or different dislocations will be there. So to reduce this SRH recombination, what we can do is, instead of having a continuous back contact, we can have point contacts. Okay, so I'll explain this also. So let's say this is the back surface we are drawing. So instead of covering the whole back, we can have dots like this. So why do you need the back contacts? First of all, we need to collect the holes, right, in the back of the solar cell, right? Just quick one drawing. So this is N, this is P. In the back surface, we have to collect the holes, right? Now the holes cannot enter into the metal because in the metal the only carrier is electrons, right? So what you have to do is whatever the electrons which are getting collected in this N type, these electrons will flow through the external circuit and come to the back electrode right here. So this electron will reach here, and then the holes which are photogenerated, these holes should recombine with this electron only in the metal semiconductor interface. Then the circuit completes, right? So we get a external current, and as well as the photogenerated holes are recombining with the photogenerated electron in this interface, right? So now there is one problem is this hole can recombine with the electron present in the p-type semiconductor, right? So p-type semiconductor, we have minority electrons, right? Minority carriers electrons are there. So these holes, photogenerated holes, can recombine with this electron present in the p-type semiconductor. Though they are minority, but still there are some electrons, right? But which we don't want. If they recombine with this, then these electrons are not essentially taking part, right? So there will not be any flow in the external circuit. So only the photogenerated holes should recombine with the photogenerated electrons which are coming through the external circuit, right? So to confirm this, or to enable this process, what we can do is we can put one p plus layer. So let me explain this diagram. So here we have n type semiconductor. This is the front surface, okay, front, and this is p type, this is the back surface. And what we are doing is we are using a point contacts. See, this is the back surface, I mean back electrode, but what we are doing is with the semiconductor the contact area is small, right? So we are using point contacts. And one more thing, this green, these are surface precipitation layer, right, to reduce all the recombinations at the surface, right? This green here also, these are surface precipitation layer. Now this aluminum metal, you can see it is coming until here, right? So it is touching the semiconductor only this region, right? Only this region. Oops, not visible. Only this region, right? So and then what we do is when we put this aluminum, when we co-fire it, or when we put this aluminum contacts, and as we hit it, some of the aluminum actually diffuse into this p type. So this automatically, this side will become p plus, right? Aluminum, if it enters into a semiconductor, so trivalent, right, it will become p plus. So this p plus made it is fabricated while making the solar cell itself. So now if you see the band diagram, you will understand this concept. So now this is the band diagram. So we have n type semiconductor, p type, and this is p plus, right? So you can see in between this this junction, which is very important now. So we have a p and p plus junction right here, and this is how the band structure, right? So so these electrons which are actually coming from, it could be the minority carriers present in this, or it could be the photogenerated electrons also. But yeah, it could be photogenerated electrons, or it could be the minority carriers electron present here. But these electrons should not recombine here, right? These electrons should not enter into this region, because we want the holes which are photogenerated, they should reach this region. Okay, they should reach this region, and recombination should take place here in this interface, and the recombination should happen with the electron which are coming from the front surface, right, photogenerated electrons, but not the electrons present in this P plus region. So we have, you can see there is a electric field here in this, right? In this direction there will be an electric field, right? So you can consider this interface which is lightly doped P and P plus, right? So effectively you can consider this is an NP junction, right? So there is an electric field present here. So this electric field will prevent the electron to these electrons to enter into this region, right? So here only the electrons will be there which are coming from this metal electrode, right, in this region. All the electrons which will be coming from the metal electron, not from this minority carriers electrons or the photogenerated electrons present here, right? So you can prevent this kind of unwanted recombinations at this interface in this region, right? So this kind of field is called back surface field. Back surface field. So this back surface field is produced because of this doping concentration, right? One is P, one is P plus. So we have back surface field at this interface, right? So we could separate these electrons, minority electrons, and the electrons which are coming from, you know, the metal contact, which is collected by this emitter layer. I mean, from the emitter layer on the front contact, right? So this concept is very important. Hope you understood this concept, right? So this is how we make the back contacts for the solar cell. And this diagram, this is one photograph. So this is for a polycrystalline silicon solar cell. Polycrystalline silicon solar cell surface. Okay, this is taken optical image. You can see it is very shiny, right? So this doesn't have any anti-reflection coating. Okay, so this is without the ARC, anti-reflection coating. And now when you put the ARC, you can see anti-reflection coating, it's become dark. It is light bluish because blue light only it is getting scattered off, only blue, but other wavelengths it is getting absorbed, and ideally it should be black in color. So that also we can make it by using by using proper anti-reflection coating. If you put it, then we can get even this surface as black. We can make this, and that is very important, and we call this kind of silicon solar cell as black silicon. We can make it by using proper, you know, anti-reflection coating. Usually we use double layer anti-reflection coating to make this kind of black silicon. Okay. Yeah. Any doubts here? Okay. So we'll move to now the fabrication of silicon solar cell, okay, or crystalline silicon solar cell. That how we make this crystalline silicon solar cell. So I've taken this diagram from our reference book, Orno Smith. Now we'll just understand the steps how we fabricate this silicon solar cell. Okay, so this thing we studied that to start with, when we grow the single crystal, whether it is Czochralski or float zone technique, we dope the silicon wafer with p-type, right? So to start with itself, we have a p-doped silicon wafer, right? So these silicon wafers, which are coming out from the Czochralski technique, and then we saw it off, right? We get a big ingot like this, cylindrical ingot, and then we slice it, right? And this is just one piece of this slice here we have. Now, while slicing, this is generally done with a wire saw. Okay, so how it is done, if you see any silicon wafer making video, you can see that there will be multiple fine thin wires which will be rotating. Okay, so it's something like this. So this wire, I'm just drawing one wire, and this wire is kind of in a loop. Okay, this wire will be rotating through the help of motor, and there will be multiple wires, you know, across it. Now you put this ingot here, and then keep pushing this ingot up. So as this wire moves, it will be keep sawing it off. Wire using very thin wire, then we'll have very less craft loss, right? When you cut something, right, we lose the material of this thickness, right? Whatever the wire thickness, that material it will be waste, right? The same case here, that's why you go for very thin wire sawing, right? And this wire distance will define as the wafer thickness, right? For our case, roughly 200 micrometer. This is the thickness, right? So the distance between two wires, we put it such a way. And now after getting this wafer from this sawing process, this wafer will have a lot of, when you saw it, there will be a lot of silicon dust, lot of rough surfaces, right? All debris will be there on the surface, so we have to clean it off. So for this cleaning process, what we do is we take two type of etching process we use. One is called alkaline in the sense more basic, right? And another is called acid etch, acidic. So depending on the pH level, right, we can choose these two etching process. So what we are doing is now we are cleaning off the saw damage by using this wet etch technique. Okay, and next we do a texturing process. So texturing is very important, and it is done here itself. Earlier we saw, right, when you do the surface texturing like this, right, we have a chance of double absorption. So straight light can be absorbed, and the reflected light can again get absorbed in this surface, right? So two times it can get absorbed, the same photons, same this ray, right? So this texturing is done here itself, and this texturing process becomes easier because the silicon crystalline silicon has a property, like when you etch it with this solution. So what we have in this, we have KOH, that is potassium hydroxide. It's a alkaline base, right? And with isopropanol. In this mixture, if you put it this wafer after this cleaning, then you get this kind of surface texturing, because for silicon, if you see the different surface etching rate, this 110 surface, the etching rate is much faster. So etching rate in the sense, when you put this wafer into this solution will react with the silicon, okay, and it will etch off, or it will take away some portion from this wafer, right? Now we are using crystalline silicon, right? And it so happened that the silicon crystalline silicon structure, the bond strength and all, so it happens that 110 surface, it etches faster compared to 111 surface. So 111 surface, if you see for any crystallographic, right, 111 surface, generally it's a diagonal surface, right? in the lattice structure if you see. So the facets it will create after removing, it will create a pyramid like structure in three-dimensional space. Not able to draw it, but you can imagine, right? A pyramid structure it will produce this 1 1. So other surface 1 0 0 they get etched off, right? So earlier it was a plane surface and this material got etched off because they fall in this 1 1 0 plane, but finally 1 1 1 surface will left off. So we get this kind of surface structuring after this weight edge, right? So we have got the pyramid structure here. Now what we have to do is we have to make the N layer, right? So we have P type P doped wafer. Now we are making the N layer. So how we are doing it? For this we we have to dope with a phosphorus, right? Phosphorus is pentavalent. It's a N type dopant, right? So for the source of phosphorus we use this POCl3. POCl3 it is phosphoryl chloride. Phosphoryl chloride, CH. This phosphoryl chloride we use in a high temperature furnace, so it is in 850 degrees centigrade, and if you pass this phosphochloride as a vapor, right, it diffuses into this surface, right, all the bare surface, this phosphorus present in this composition, it will diffuse inside. And now depending on the time we give in this furnace, we'll have we can control the thickness of this N layer, which is very critical again, right? We need roughly 0.3 micrometer diffusion length, right? So when you do this process, what is happening is it not only creates this N layer, but it also creates this phosphate silicate glass, right? It's a byproduct. So phosphate silicate glass, it's a mixture of so some of the phosphorus it will be P2O5, and some of the silicon also get oxidized as SiO2. So this forms a glass called phosphate silicate glass, and generally this is very insulating in nature, right? It's a glass. So we need to remove of this layer, which you don't want. It's a byproduct, unnecessary things. So for that, what we do is we put this wafer into this HF solution here, hydrofluoric acid, very corrosive acid, we all know, right? Very corrosive. You have to handle it very carefully even if you use in lab, right? So when you dip it here, in a few minutes, it will etch off this PSG. Maybe few seconds it's enough. So again, depending on the acid concentration, the H rate matters, but HF generally the reaction is very fast. So any glass you put in this HF, it just etch off, or it will react with it, right? So it will take away this PSG, this phosphate silicate glass, the outside layer. You can see this brown color, it will etch up. So now what we have is we have the middle, we have p doped silicon wafer, and the yellow slight tint you can see, this is the N-type layer, right? Now we need the precipitation layer, right? Surface precipitation layer to reduce all the recombinations, or anti-reflection coating. So what you do is we put silicon nitride here. How you put the silicon nitride we already discussed. We use plasma enhanced CVD, right? Plasma enhanced chemical vapor deposition. So with this technique we put this silicon nitride layer because it has got refractive index roughly 2.1, right? So which is good for anti-reflection coating, as well as it pacificates the surface as well, right? No dangling bonds here. Now if you notice carefully, then we have the silicon nitride layer on the top, but the bottom also we have N type, right? So we have NPN, right? This structure here we have NPN structure, but for working of a solar cell we need N and P structure, right? NP junction. This bottom N layer we have to remove, so that is again removed with some acid HF. If you put some high concentrated HF, we can remove the back N layer, right? So here we are removing this back N layer. Now we have in this process here we already have this PN junction with the front surface specification, right? Now what you have to do is we have to make the contacts. Okay, we can put this silicon nitride also in the bottom if you want to passivate the back surface, but front surface specification is more important, right? Yeah. So we have the PN junction with the front surface specification. Now we need to put the metal electrodes top and bottom, right? So ideally for the top electrode we go with top electrode we use generally silver. Generally silver is preferred, and for the bottom is aluminum electrode. Why? Because aluminum will act as p-type dopant also. So this putting this electrode on the top, so this is we are doing by help of screen printing technique. Okay, so as you can see here, screen printing technique, what we have is we have this one metal mesh kind of thing which has got all these rulings, right, the openings. Now when you put the paste on top of it and roll it, right, then what happens, this with this opening the metal get deposited only at that opening point, right? So we can have the pattern as per our requirement, right, which we have decided earlier, that what should be the usual thickness of bus bar and fingers, right? So accordingly we create this mesh. Now we put the silver on the top and we put the aluminum on the back. Then what we do is we co-fire it. Co-firing in the sense, so both the pastes are put on the on the wafer. Now this paste will contain polymers in it. So and the adhesion between this paste and this wafer, it will not be so good at the beginning. So what we do is we dry it off first and then we put it in a furnace here, right? It's a belt furnace, so it is rotating like this, so it enters here and then we get the wafers on the other side, and it is kept at 850 degrees centigrade. So at this high temperature, what happens is in this paste it will have some polymers, some bonding materials, so those polymers and all will burn away, so it will leave only the metal on the surface after this co-firing technique. Why we are calling co-firing? In this process we are firing front and back contacts together. Sometimes we do it separately depending on the process, but co-firing means we are doing or we are curing both the electrodes together, okay, front and back. So in this process two things happen. One is the silver paste, what it happens in the front surface is it etch off this this yellow is our N layer, but we have this silicon nitride layers also, right? Here as you can see, this black is silicon nitride layer, right? So this silicon nitride layer get etched off by this silver paste, whatever the composition it has got. So directly this silver paste will sit on the N-type layer. As you can see here, this black, which is silicon nitride, which is again an insulator, right? So we don't want that in between metal and the semiconductor. So it get etched off by this process. So metal will sit directly in contact with the n-type silicon here in this, you can see. And in the back contacts, so in this diagram it is shown as full, right? But sometime depending on the back contact process, we sometimes put dots also, but here it is continuous. In this diagram it is shown. So what is happening in the back contact then? So back contact we are putting we use aluminum paste. Okay, now this aluminum paste, what it will do is when you co-fire it, some of the aluminum in this process, some aluminum will enter into the P type, right? It will diffuse. So we'll get a P plus layer. This blue layer you see, it is a P plus layer, the dark blue. So we got this P and P plus layer formed here, right? That back surface field. This is also done in this process. And last thing is we have to isolate from this front and back, right? So when we do all this doping and all, and this metal electroding, there should not be a leakage between the front and back, right? Especially the sides of the wafer, right? There could be some spillage, right? So that has to be removed. So what we do is we put some isolating groups by using some laser, my high power laser. So we'll be just screwing it or make this kind of groove so that there is no direct contact between the front and the back surface, right? They should be insulating, right, from outside, from this surface side. Otherwise there could be a leakage, right? If let's say while printing or when we make this kind of doping and all, there could be some connectivity between these two, right, front and back. So which is removed or ensured that they're not there by doing this isolating groups by laser, kind of laser etching. Okay, so now our silicon solar cell is ready here. Here the cell is ready, and of course we need to make panels from it. So for that we'll learn later that how we decide series parallel combinations to get a useful output from the cell, because in this cell the dimension will be just a couple of centimeter or couple of centimeter by centimeter, maybe 6 centimeter 6 or even 1 centimeter 1 centimeter, depending on the cell we make, right, the wafer size. But the effective current will be very poor, right, depending on the area. We know, right, it produces roughly 30 milliamps per square centimeter, right, which is nothing for daily use, right, this amount of current. And also the voltage it produces around 0.6 to 0.7 volt, right, so which is also not very useful, right, directly. So we do series parallel connection later on to get a usable voltage and current level. Any doubts in this wafer making process? No. Okay, no more doubts. We can move to 47. Now, next topic is a few high efficiency concepts. It's not going. Got stuck. Okay, anyway, it will take some more time also. It's already 50. Yeah, we'll stop it here today. And next class, we'll continue with a few high efficiency concepts for this solar cell. Okay.